Hi everyone, I'm Sruthi Erra Hareram, and today we are going to end on Cube Native ETL at scale, specifically how to make PySpark plus Airflow fast, reliable, and cost efficient in a cloud native environment. So I'll start with the architecture that keeps us stable, then the spark tuning that actually moves the needle, then the orchestration patterns that reduce operational pain, and I'll finish with the phased rollout you can start next week. My goal is zero fluff and maximum practicality. Let's align on the route and we'll take so each section builds on the last. Here's the agenda, and we'll move through 5 building blocks. So the first one, the cloud native ETL architecture, where we'll discuss the containers, Kubernetes, and the IAC. So we stop the firefighting environment. Second, the PySpark performance optimization, where we'll talk about the memory, join, and strategies and how to take. Third, the airflow orchestration techniques, where we have the dynamic tags, resilient patterns, and monitoring to stay ahead of failures. Fourth, a real world scale, what a multi terabyte pipeline would look like when this is done well. Fifth, an implementation roadmap, phased steps to adopt safely without risking production. Before the how, let's be honest and discuss about why, what breaks at the scale. These are the ETL scaling challenges that we face, and when the data volume and the velocity climb, the same 4 issues resurface. One, the resource misallocation. So clusters are either over provisioned or expensive, or under provisioned and unreliable, because sizing is guesswork and provisioning is slow. Two, limited visibility and complex dependencies. When a job fails at 2 a.m., you can't see lineage or timing clearly, so recovery is manual. Three, there is brittle monolith. So small changes like a new column can ripple through a monster script and break everything. Four, exploding data volumes. More data increases shuffle cost, storage cost, and blast radius of bad input. Together, these cause delays and unpredictable costs and reactive firefighting. So, a better way is agile, automated, and scalable architecture. Resources flex with load, dependencies are explicit, and reliability is a feature, not luck. Let's pour a stable foundation first, and then we'll talk about speed. So, we rely on 3 mutual reinforcing pillars. So, the first pillar is the container. So, where here the code is packaged and dependencies together. So, the jobs are reproducible across dev, test, and prod. That alone eliminates the works on my machine surprises and lets each pipeline declare exactly the CPU, memory, and the JVM it needs. Pillar number 2 is Kubernetes as a compute fabric. So namespaces isolate teams, autoscaling expands worker pods, under loads and quotas keep noisy neighbors in check. For multi-tenant analytics, this is essential. Number 3 is the infrastructure as code. We've used Terraform and this helps to deploy the platform and Airflow declaratively. So we can review the changes via requests and promote via GitOps. Turns infrastructure into version and testable artifacts. Here's a quick example. So, if a team needs a Python upgrade or a new connector, you ship a new connector container and roll it out safely through Helm values. No snowflake service, no drift. With the runway built and the plane is sparks, let's tune it to fly. So the spark performance reduces to 3 layers, right? So the first is memory, then the joins and skew. When it comes to memory, you can start by right sizing the executors. Approximately 4 to 8 GB per executor is a pragmatic range. Cache sparsely with persist only where reuse pays off. Set memory fractions around zero point 0.6 for execution and zero point 0.2 for storage as baseline. Adjust with real metrics, not hunches. Then coming to joins, use broadcast hash joins for small dimensions for about like less than 100 MB. Two steps, side step shuffles. For large fact to fact joins, lean on sort merge and reduce the number of byte stage. If you see ballooning shuffle read times, your join strategy is usually the culprit. Then coming to this queue, a handful of hotkeys can stall an entire job. Use salting or pre-aggregation on hotkeys to so the partitions finish at similar times. Reliability touches. So add checkpointing to cut lineage depth, right? And enable predicate pushdowns and dynamic partition discovery to trim I/O and make all writes idempotent. K8s aware retries don't double writes. So here's a mini story. We had a dimension table at 60 MB moving to broadcast join at a stage from 19 minutes to 3. Another pipeline had a single customer representing 40% of the rows. A simple salt with 16 buckets leveled the partition and removed the straggler. But don't trust vibes, prove it. So always take a baseline. So driver or executor counts, right? Memory, shuffle read or writes, stage times, and spill metrics. Change one variable at a time. You'll typically see wins from fewer shuffle and better executor sizing and smarter joins. When you confirm a win, bake it into the project templates. So the next pipeline inherits the improvement by default. Now let's orchestrate at scale without turning SRing into a midnight hobby. So here's like the Airflow on Kubernetes. So running the Airflow on Kubernetes aligns the control plane with data plane. You get scheduler scalability to 1,000 plus DAG runs per day, pod level isolation. So each task declares CPU and memory, workload identity, and managed secrets for built in security, and cloud native logging or monitoring out of the box. In practice, teams around 99.9% scheduler uptime with drastically less operational overhead. So, here's a practical tip you get to define a small set of pod templates, a small IO, heavy joins, and machine learning. So, tasks pick the right shape by convention. So, orchestration is more than just scheduling, and it's patterns that scale people. So, here are the few advanced airflow patterns for resilient ETLs. Adopt these four patterns to raise reliability without raising head counts. First one is the dynamic tag generation. So, keep the config in S3 or JCS and programmatically generate the tags. Hundreds of similar pipelines with minimal copy paste. Second is the intelligent branching. Here you can use a branch Python operator to route around known bad data or to choose the light path versus the heavy path based on the input sizes. 3. Backfill design. So drive jobs by logical run dates. Make each step idempotent and separate compute from storage so old runs can be preprocessed safely. 4. SLAs monitoring. Be custom callbacks into Datadog or Prometheus. Alert on lateness and on leading indicators like raising retries, not just the failures. So here's a micro example. A media pipeline checks volume at a fan in step. If today's volume is greater than 1.5 times the day 7 median, it auto branches to a wider executor profile and adds a midstream checkpoint. So, of course, all of this still lives and dies by the executor sizing. So here is a chart of the Spark executor's sizing. It is basically the art of the resource allocation. Think of the sizing as a curve, not a point. Large executors mean fewer JVMs and strong throughput, but risk long GC pauses and amplify skew. When coming to the medium or balanced, executors are good default for mixed workloads. Tiny executors start fast and pack the cluster with parallelism, but management overhead and shuffle plan out can dominate. Your safety net is dynamic allocation with sensible minimum or maximum bounds. So the cluster scales under load but never crashes. Target the sweet spot where utilization is high, spills are rare, and shuffle stages don't bother. Here's the field trick. If median task time is low, but the P95 is awful, suspect skew. If both median and P95 are high, you are under resourced or over shuffling. You can't tune what you can't see. So let's wire observability in from the start. So here's the monitoring and observability. And this is actually the reliability foundation, as you can say. So it comes down to the metrics. So use Prometheus to capture cluster health and Spark app metrics, watch executor active time. Shuffle read bytes and spills and task skews. And then logs and traces. Emit structured JSON logs with correlation IDs. Add OpenTelemetry tracing to switch Airflow tasks and Spark stage into a single story. Data quality. Automate profiling with great expectations and get critical steps on expectation suits, alert on KPIs the business cares about, not just the technical counters. Costs, track the per app and per tag costs so you can right size continuously. Now we've got the what and the how. Now, how do you adapt this without breaking production? So here's the modernization journey. Here you can, following this from phase 1 to phase 5, you can build a legacy batch to a cloud native ATL. Use the 5 phase path so risk stays low and momentum stays high. Phase 1, assessment. Here you can inventory jobs, profile performance, map dependencies, choose candidates by business impact. And phase 2 is the containerization. So this splits monoliths into modules, packaged with multi-stage Docker for smaller, faster images, and followed by orchestration. So clean DAG dependencies and manage environment-specific configurations via Airflow variables. And for optimization, right size, tune joins or memories, and reboot, retry, or recover. And coming to operationalization, we can use CI/CD, monitoring, SLAs, documentation, and knowledge transfer. Small bet approach. So migrate one medium impact pipeline per sprint, compare baselines versus new, publish the win, repeat. Now, as you roll out, dodge the classic traps. So we have the common pitfalls, and it's better to avoid them. So the first one is the resource misallocation. Over provisioning wastes money, and under provision fails jobs. Enforce dynamic allocation bonds and alert on idle time. Excessive shuffling. Often skew or unnecessary repartition. Use Spark UI and stage metrics to pinpoint hotkeys, salt, or pre aggregate wrong formats. So switch large datasets from CSV or JSON to Parquet or ORC for 3 to 5 times the gains through columnar storage and compression. For orphan resources, failed jobs can leave like pods or persistent volumes, and add cleanup hooks and quotas as guardrails. So let's land this with a concrete starter plan and three messages to remember. Here's the implementation roadmap if you are planning on getting started. So this is how your implementation would look like. So week one, you can pick on safe pipeline, record baseline runtime, and shuffle and cost. Week two, stand up a small K8s node pool, deploy airflows with Helm, set workload identity secrets. Week three, containerize the pipeline, add dynamic allocation, switch joins appropriately, and add checkpoints. Week 4, wire metrics, logs, or quality checks. Run new versus legacy in parallel. Compare and publish results. Capture lessons in Spark or Airflow playbook. And if you only take three ideas with you, here is the key takeaways. The key takeaways are architectural discipline, performance optimization, resilient orchestration, and operational excellence. Coming to the architecture first, it depends on the containers, Kubernetes, and the IAC. This gives the stability and speed of change. The PySpark tuning pace. So, focusing on memory, joins, and skews routinely yields approximately 30 to 50% of efficiency improvements. And then coming to the observability, trust or metric logs, traces, quality, and cost visibility makes pipeline dependable and defensible. Thanks for spending this time. And if you would like the sizing templates, dynamic DAG patterns, or migration checklist, I'm happy to share. Thank you so much.